All right, we left off in about 1808 with Dalton's atomic theory. At this point, we know that our atoms are indivisible, that all atoms of a given element are the same, that somehow different elements or the atoms of different elements are fundamentally different. We know that compounds are two or more elements in a fixed ratio, and we know that in a chemical reaction, atoms just rearrange. So let's go ahead, almost 90 years, and look at the discovery here of our subatomic particles. Let's go inside the nucleus. What do you need to know here? You need to look at how we got our nuclear model out of this, and we need to know which experiments and who actually did the experiments to get there. Then we need to look at atomic structure such that we can understand atomic number and mass number and discuss our isotopes. Okay, so leaving off after about 1808 and going to the late 1800s, we need to look at the work of J.J. Thomson. Now, J.J. Thomson was working with a cathode ray tube, and he was pretty much playing with it and looking at what it does. Cathode ray tube, this shorthanded as a CRT. These are the old-fashioned screen monitors or the old-fashioned televisions, the one with the great, really heavy ones that aren't flat with the great big things sticking out the back. That is a cathode ray tube, so your grandmother may have had one. Now, what would you have in a cathode ray tube? Well, you have a piece of metal as the cathode and another piece of metal as the anode, and you put on very high voltage. When you put on high voltage, we know or knew that things came out, and these things that came out were called cathode rays. And when you put it on a fluorescent screen, it glowed. And you went, okay, fine. Well, J.J. Thomson wanted to know more about the cathode rays. Now, they understood a great deal about the interaction of electricity and magnetism before J.J. Thomson did this experiment. And what he did was he put a magnet such that it could interact with these cathode rays. And when he did that, he found that the cathode rays deflected. And he said the only way for that to occur is for the cathode rays to be charged, right? So that what they were was a electronic, they were ions, they had a positive or negative charge. And not only did he know that they were charged, he also knew that they had to be a negative charge. And then he said, okay, we've got these negatively charged things that come out of these cathodes or these anodes, and we put on this high voltage. So what are they and where do they come from? So he came up with his model. Now, we are all men and women of our time. So when he suggested this, he called it the plum pudding model. Well, what's the plum pudding model? It's really pretty much a raisin cake. So he said that the electrons are the raisins and the cake itself is whatever is left over. Well, he said if electrons come off, these negatively charged particles, and again, he could tell that from the direction that the cathode rays moved when the magnetic field was applied. So if these negatively charged particles came out, it would be like picking the raisins out of a raisin cake. And if there was something negative, there had to be something positive left behind. So these came out, and the positive stuff was left behind, and he called it the plum pudding model. Now, we would probably call it the chocolate chip cookie model because we took the chocolate cookies out, or the chocolate chips out of our chocolate chip cookie. All right, so after that, it went on to the work of Millikan. Now, Millikan, through a pretty slick experiment, which was his oil drop experiment, found the charge on the electron, and he calculated the mass of the electron, the details of which we're going to leave. So let's make sure we understand. J.J. Thomson found that cathode rays were negatively charged particles, that they are inside the atom, and Millikan, discovered their charge, the actual charge, not just that they are negative, and found the mass. So we now call these particles electrons. J.J. Thomson discovered them. Millikan figured out what the charge and the mass was on them. So what do we have left now? What we have left is the positive stuff or the cake that is left behind. Well, Ernst Rutherford decided he was going to explore what was left. And so what he did was he took an alpha particle emitter. An alpha particle, by the way, is a helium atom stripped of its electrons. Now, this helium atom is coming sailing out of the hole or a slit that is inside of this emitter. Now, this is radiation. This is very dangerous. And what he did was he shot it through a sheet of gold foil. Now, why gold foil? Gold foil is so malleable that you can hammer it into sheets that are so thin you can see through. So it was like a piece of tissue paper. And he shot helium atoms or helium ions through this sheet of gold foil, like this sheet of tissue paper. Now, note that these were moving at about 10% of the speed of light. So the speed of light is 3 times 10 to the 8th meters per second. So these were about a tenth of that, which tells us we are moving pretty damn fast straight through a piece of tissue paper. All right, so what did he find? Well, if this was a plum pudding or chocolate chip cookie model, all these particles should have gone straight through. Well, what he found instead was virtually every single particle went straight through and occasionally one bounced back. A little bit of deflections, but mostly straight through and one bouncing back. So what does that mean? Well, the one that bounced back had to have hit something. That's the only way that it could have bounced back. Well, the key is not that it hit something, it's that the rest of it missed them. So if every, let's say 19,999 missed or were slightly deflected and one hit it and bounced back, whatever this thing hit right here had to be very, very, very small. And he said, okay, most of the atom has to be empty space, and all of that positive stuff has to be in a small, dense center, which he called nucleus. Now, this nucleus is tiny, so let's try to understand how tiny this is. If the nucleus were the size of a raisin, the atom would be bigger than a sports stadium. Okay? Size of the atom. And everything in between the raisin or the nucleus and the edge of the sports stadium is pretty much empty because those alpha particles could go straight through. So what do we know? Well, we're going to not discuss the final experiments looking at the proton and the neutron. Again, what do you need to know? You need to know Lavoisier. You need to know Dalton. Lavoisier proposed that mass was conserved. Dalton put it all together in its atomic theory. You need to know that J.J. Thomson discovered the electron. You need to know that Millikan figured out the charge of the electron and the mass of the electron. And you need to know that Ernst Rutherford discovered the nucleus. He said that the rest of the remaining mass of the atom is in one tiny dense center. All right, so with that, we need to look at these subatomic particles. So the only ones that matter to chemistry, and there's only three, are protons, neutrons, and electrons. Proton, we're going to shorthand as a lowercase p. An electron, we always put an E minus to remind us to keep track of the charge. And a neutron is a lowercase n. Now, the mass of the proton and the neutrons, while tiny, are almost identical, of about 1.67 times 10 to the minus 24 grams. We're going to also use units of AMUs, but we'll do that in the next section. The protons and the neutrons are inside of the nucleus. The proton has a positive 1 charge and the neutron has a 0 charge. The electron is in that, quote, empty space outside the nucleus. Every one proton, in terms of our subatomic particles, we are going to have one electron for a neutral atom. The number of neutrons can vary. The charge on each electron is -1. So if you have an atom that has one proton, that's a positive one. If it has one electron with it as well, which it will if it is neutral, that is going to have a charge of -1, and the net charge on your element will be 0. The number of neutrons, again, is variable. All right, so let's put this together. We have protons, and we have electrons, and we have neutrons. We know the protons and the neutrons are in the nucleus. We know the electrons are outside. And we are going to define the atom by the number of protons. So if it has one proton, it is a specific atom. If it's got two protons, it's going to be a different atom. And these are the numbers on the periodic table. So for example, if you see hydrogen with a little 1, it's the first element you find on the periodic table, that means 1 proton. All right, that number, the number of protons, is symbolized by a Z, and it is called the atomic number. So for example, if we have helium, all helium atoms have an atomic number of 2, and they have 2 protons. If our helium atom is neutral, it is also going to have 2 electrons, and the number of neutrons, again, is variable. So the next term is the mass number. The mass number, we're going to shorthand as an A, is equal to the number of protons plus the number of neutrons. Now, we always know the number of protons from which element it is. And so when we discuss an element, we tend to, instead of saying that we have, for example, helium with 2 neutrons, what we say is that we are going to have helium-4. What do we mean by that? Well, we know if we have helium, it has 2 protons. And if we say that we have helium-4, what we do when we write the symbol for our isotopes is we put the mass number here, we put the atomic number here, and if we name it, we name the element, followed by the mass number. So if I had helium, all isotopes of helium, all atoms of helium are going to have 2 protons. That's our atomic number. One of the options for this is going to be a total of 4 in terms of summing up our protons and neutrons, 2 protons, 2 neutrons. And so we would call this particular isotope of helium, helium-4. So that is going to be the sum of the protons and the neutrons, and again, the number of neutrons is variable. So define an isotope. An isotope, or isotopes of a given element, have the same number of protons, same atomic number because they're the same element, but different numbers of neutrons. The numbers of neutrons can only be determined by experiment. We have no theory that explains it well. And what we do is when we have a symbol for this, we're going to take and put the mass number, which again is the number of protons plus the number of neutrons, on the top of the symbol. So if we had 14C, we had 12C, first of all, we'd name this as carbon 14. We'd name this one as carbon 12. And if we want to look at what we have here, so if we have 14C, we know that carbon always has 6 protons, so we can put that number down there. Please note that this number 6 is optional. It is, if we have carbon, we always know that it's going to have 6 protons. So if you like, you can completely leave that number there. But if you want to put it in, that's absolutely fantastic. And again, isotopes are atoms of the same element. That's the symbol here in the middle, with different numbers of neutrons in their nuclei. So what do we have? Well, if we have 14 carbon, 6, and we're going to be neutral, meaning the number of protons is equal to the number of electrons, then we're going to, in this atom, we're going to have a total of 6 protons, 6 electrons, and if we take the top number, which is the number of protons, plus the number of neutrons, and we subtract 6 here, number of protons, we're going to get a total of 8 neutrons. If instead we have carbon 11, we're going to have 6 protons, 6 electrons, and 5 neutrons. So let's finish up this concept. If we finish this up and we take a look at this, if we have 20 protons, we can go at our periodic table, realize our atomic number is 20. If this is neutral, again, this is given as neutral, our number of electrons is also 20. Our mass number is the sum of these two, and this is going to be 40. If we've got 20 protons off the periodic table, we're going to realize that that's calcium. We're going to put the mass number on top, and that's 40. And we can put the atomic number down there if we like. 53 electrons. Well, if we have 53 electrons, then we are going to have 53 protons, and our atomic number is also 53. Now, if we want to know how many neutrons we have, we are going to have to take and do the math. And we're going to have to take 131, our atomic number, and we're going to have to subtract 53 from it, and we're going to get a total of 78 neutrons. Now, again, the number of neutrons is variable. This happens to be a radioactive isotope of this element. If we have the element 53 and we go to the periodic table, that's iodine. We can put the 53 down here, and we put the atomic number 131 up on the top. So, continuing, if we have aluminum here, and we got a 13, we know A, if it's aluminum, it's always going to have 13 protons, which means that we have 13 electrons, and we have an atomic number of 13. If we are looking at the number of neutrons, that's going to be 27 minus 13. That's going to be 14 neutrons. If we have 14 neutrons here, and we're given that our mass number is 27, again, the number of neutrons plus number of protons, we get this element. So atomic number 55. If we have atomic number 55, we have 55 electrons and 55 protons. If we take the mass number 133 and we subtract the number of protons, we're going to get the number of neutrons. And by the way, you could have the same number of neutrons for two different elements. The only thing that is a fixed value is the number of protons. The number of protons gives us the element. So this is cesium. Again, off the periodic table, if you go up and you want to put the mass number, it's 133. If you want to put the atomic number down here, is 55. If the element is neutral, the number of protons and the number of electrons are equal. The number of neutrons always has to be found by experiment.